In problems 45 through 50, we're talking about the mean value theorem for integrals. So I want to spend a couple of minutes to discuss what we mean by the mean value theorem of integrals. So let's assume that we have a graph, and it's between two x values. We'll call them x equals a and x equals b. Well, obviously there's some area under that curve there. Let's shade that in red. And we know that the area of the shaded region would be given by the integral from a to b. And again, we're going to assume that this curve is f of x dx. So that's that area there. But we know that all area can be shaped into a rectangle, for example. We could take that same exact area. We're not going to change the area there, but we're going to shape that area into a rectangle that happens to have the same base, that is from a to b. So that area, when we shape it, might look something, or that rectangle might look something like this, where we're going to have a little bit of area that's outside of the rectangle, but under the curve. That would be up here. But we also have some area that's inside the rectangle that's outside of the curve. And so at some point it's going to match up. At some point those two areas have to be exactly the same. Again, you can think of just raising this bar little by little. That would not equal the area. That would not equal the area, the red area. That would not equal the red area. And if we went all the way up to the top here, this would be more than the area under the curve. So we know that somewhere in between there is a horizontal line that gives us the top of that rectangle that has exactly the same area as under the area under the curve, that is the red shaded area. So at some point the blue shaded area will equal the red shaded area. Sort of like so. At some point there is a height, and if you notice, that height will always be the y value of a point or points on the curve of f of x in between a and b. It has to be somewhere along the curve there. So what we're going to do is we're going to call these, it doesn't matter which one we use, we're going to call this C. So what we want to do is, or the height of the curve when x is equal to c would be f of c. Now we can put this together and say that we have an identity here, that the area under the curve, that is the integral from a to b of f of x dx, has to equal the area of that rectangle. Well, what is the area of a rectangle? It's just base times height. And the base is the length from a to b, so we would call that b minus a, and the height would be f of c. And so this is what is called the mean value theorem for integrals, where the area under the curve between a and b has to equal the area of a rectangle with a base from a to b and a height that is somewhere that crosses the f of x curve at some point. So what we're asked to do in these cases, in these first few problems, is to find the value c. So that's what we're looking for right down here. We want to find the x value where that occurs. So the quantity on the left, the integral from a to b of f of x dx, well, that's what we've been doing all along. B and a and b are both known, so b minus a, that is the length from a to b, is also a constant. That's a given. And so all we're going to do then is to find that value set the function equal to that and solve for x. So we'll see what that means. So let's look at what the left side of this looks like. And we'll work with number 45. So we have the integral from 0 to 3 of x to the third dx. And that is the antiderivative. We're going to do this exactly as we've been doing all along. X to the fourth over 4 from 0 to 3, and evaluating 3 to the fourth power. 3 times 3 is 9, times 3 is 27, times 3, that becomes 81 over 4. Plugging in 0, we're going to get 0. So the left side of this is equal to 81/4, the total area under the curve, or the red shaded area, if the red shaded area would also include going all the way up to the top of the curve there. So the red shaded area, we know in this case, is 81 over 4. Well, what is b minus a? B minus a is 3. So we have 3 minus 0. And here we'll just call this f of c. So we know that these two quantities have to equal each other. Well, that's just 3 times f of c. And if we were to divide both sides by 3, we would end up with, now, let's carry this down, three times f of 3. Now, so at this point we're going to start changing things around. We divide both sides by 3. We get 81 over 12 is equal to f of 3. So what do we mean by, f of c? Sorry, the 3 should not be mixed up with the c's there. So we know that f of c, in this case, the height of the function that gives us that defines a rectangle that has equal area to the area under the curve from a to b. That height is 81/12. Now what we want to do is find out, well, what is the x value where that occurs? Well, we know that our function is x cubed. And we could call that c cubed if we wanted at this point. Remembering that c is just a value of x. When we plug in c into the function x cubed, we get c cubed. We know that c cubed is 81 over 12. And all we're going to do there is take the cube root of 81 over the cube root of 12. Actually, we can rewrite it this way. And before I do that, I'm just going to simplify that fraction. I can see that the numerator and denominator are both divisible by 3. And so I'm going to get 27 over 4 there. So I want the cube root of 27 over 4. We know that the cube root of 27 is 3. So it's 3 over the cube root of 4. I will go back and verify all this using the calculator. Now, that's fine. It's just an interesting question here, is how do you go about rationalizing that denominator when it's a cube root? You're not going to multiply it by another cube root of 4. What we need to do is we need to produce a radicand that is a perfect cube. So to do that, we would simply multiply by cube root of 2 over the cube root of 2. And that's going to give us now cube root of 8 in the denominator, which is 2. So that ends up being 3 times the cube root of 2 over 2. And we'll bring in the calculator now to see what this all looks like. Alright, so our function is x cubed. And we want this from x equals 0 to x equals 3. and at 3 to the third power is going to be 27. So our window needs to be a little bit high, not so wide, but a little bit high. So we're going to go from negative 1 to positive 4 by 1s for the x values, and then from negative 5 up to, say, 40 by 5s for the y values. And let's graph that and see what we get. So that's our graph, and the area under that curve from 0 to 3 gives us 20.25, which we said 81 over 4. 80 over 4 would be 20, and plus 1/4 would be 20.25. So that's the area there. So what I want to do right now at 20.25, what I want to do is I'm going to, bring the calculator back. What I want to do is clear that. So I'm going to Second, Program, and Clear Draw to clear the shaded region. Now I know that there is a height of a rectangle that happens to be at 81 over 4. So what I'm going to do is put in another function, 81 over 4. That's just a straight line, or 20.25. Now when I graph, you're going to see that that gives me two curves there. And what I'm really interested in is where those two curves intersect. I'm looking for the x value right here, where the curves intersect, where the height of the function is equal to 80.25. Now you should note that I have 20.25. 20.25 times 3. So I apologize. What I'm looking for here is not, I don't want to put in the 21.25. I need to put in the 81 over 12 and find out where that is equal to the height of the curve. So I'm going to go back and just change this real quick here. I'm going to graph the two functions, and so there we go. And at this point, the rectangle formed by a base of 3 and a height of 81 over 12 is equal to the area under the curve, which is 81 over 4. So let's see where those curves connect or intersect. So this time we're going to use Second Calc and the intersection function, which is 5. It asks you to select the first curve, which is the cubic function. The second curve, which you can see it highlighted there, is the horizontal function. And then guess, we hit enter, and it tells us the place where that happens is when x is equal to 1.889, etc. Now we'll know we're correct if what we have, 1.8898, is equal to 3 times the cube root of 2 over 2. So I'm going to go back out to the home screen on the calculator and put in 3 times the cube root of 2, and we can say that that is 2 raised to the 1/3 power, and we want all of that divided by 2 and a drum roll, and we get 1.8898 exactly. And so this was the confirmation using the calculator, and the way we did that was we found our area using the integral, and that's all done in red over on the left. Then we calculated the base of the rectangle, which is 3, and we divided both sides by 3 to get f of c is equal to 21 over 12. F of c is just the function evaluated at c, that's c cubed. Set c cubed equal to 81 over 12 and solve for c. We'll go on in the next video.